Okay, so off we go. So chapter 4, we're going to cover all of chapter 4 today. 3 whole sections, that's right. Strap your seatbelts on. So here's the good news. Most of chapter 4, all about optimization, most of it is just like it is in single variable calculus. So that's why we can make this pretty algorithmic in most cases. Yeah, question?
This is on the test Friday, right?
It's all fair game.
This?
Yeah, that's on the lecture schedule. There's no other time. There's no other time.
Wait, the final or the midterm on Friday?
She asked about the midterm.
Okay.
Yeah. I mean, I understand. But I mean, again, that's the last day of class. I don't really have any other options. Okay, so diving in. Again, reminder. So very algorithmic, very much like single variable calculus. Right. So I'm going to start off with in section 4.1. There's a lot of talk about Taylor series, and Taylor series is a single variable calculus thing. I hope you all remember Taylor polynomials in particular, and here is the formula for the Taylor polynomial. Now, why do we care about the Taylor polynomials? I guess anyway, it can be phrased in different ways. Here's the take that I like the best. This is the function that best mimics. This is the polynomial that best mimics the function. Right? So in other words, it's got the same value as the function. It's got the same derivative at the point A, at least. It's got the same second derivative, third derivative, et cetera, and all the way out to what we call k. This is called the degree. And it mimics f in value and derivatives all the way out to the kth derivative. In other words, it's the best mimic, right? It's copycatting f. In all of these senses, as best as possible. Okay, all right, so there is a multivariable Taylor polynomial as well. And it's harder to write down because there's multiple variables and there's, it's a lot to say, right? We're only, in fact, going to talk about the degree 2 Taylor polynomial. But the idea is just the same as it is in single variable calculus. This is the function that mimics f in value at A, in first derivatives. Now, wait a second. These are partial derivatives now, so there's actually several. There's however many variables you have, right? There's a bunch of different partial derivatives, and this Taylor polynomial has to mimic f in all of these partials. And the second partials, and the third partials, and the fourth partials, et cetera, all the way out to the kth partials. So there's a ton of requirements. And that makes it look like a really hard problem. Here's the good news. It has a really easy answer, and in fact, it even kind of looks like the degree 2 Taylor polynomial for single variable functions. You start with the value of the function, sure, right? Derivative times x minus a. It's just like in single variable. Okay, to be fair, now the derivative is a matrix. Now x minus a is a vector, right? But structurally, still derivative times x minus a. And then there's a second order term, we call it, and I'm going to say this kind of looks like the single variable version in the sense that there's a 1/2 in the front, and you can see there's 2 factors of x minus a. It's kind of like an x minus a squared, but of course these are vectors. There's a dot product in the middle, and there's a matrix in the middle, so it's not exactly what you might guess, but it's not far off. And then, furthermore, this, playing the role of the second derivative, if you look at this matrix, it is just the matrix of all of these second partials. So it's kind of a second derivative, if you will, kind of abusing the term, but not an unreasonable take. Right? So highly analogous to the single variable version. So you just need to make sure you know this formula. It's a good idea to plug and chug a few examples. We are done with 4.1. All right, now we're going to move on to 4.2. So, quick review of single variable optimization. Now, again, this is kind of old news. So let's look at the following list of conditions. three things that we might know about a point in the domain of a function that maybe I want to optimize. I want to find the maximum possible value, the minimum possible value, whatever. And I claim that we know these three things about, for example, a point that looks like this. At that point, notice that is an interior point in the domain. It's not a boundary point. The function, at least according to the graph here and the inferring as implied from the picture, function's differentiable there. And the value of the derivative is not 0. You can see there's kind of a steepness. I claim that whenever you know these three conditions, then you can instantly conclude this is not the maximum we are looking for. How could it be? How could this possibly be the maximizer? Look, the it's increasing as you go to the right. Couldn't possibly be the maximum. It's steep there. Right? This is kind of a freebie idea that this could not be the maximizer that we're looking for. So I'm coloring green, not because it's not what we're looking for. You'd think it's a bad thing, not a good thing. I'm coloring it green because these are points where we understand with confidence what we can say about this point. Right? I know with confidence. It would be nice if I knew with confidence that it is what I was looking for, but that's not the case. But we at least do know what it is happening at that point. And good news, we know what's happening at most points in the domain. Most points in the domain for most functions. Now, not every point. Right, there are some points where I do not know these assumptions that I need. So, for example, there might be a point that's not in the interior, or a point where the function is not differentiable, or a point where the derivative is not 0, otherwise known as 0. Right? So, if any of these things happens, I'm coloring these in red because this means that my argument about, hey, check it out, it's steep, it couldn't possibly be the maximizer, that argument fails. Points that satisfy any of these three conditions, I don't know. I don't know what's going on at those points. Maybe they're maximizers, perhaps. How would I know? I just can't eliminate it based only on what I'm seeing in the algebra here, right? So points like this, these are the boundary points. I don't know what's going on there. Points where there's a differentiability issue, points where the derivative is 0. At those points, I cannot conclude instantly that these are not the maximizer we're looking for. So single variable calculus's approach to this situation is to say, all right, well, we're going to call these critical points. Any point that satisfies any one of these three conditions. In other words, any point that fails our elimination argument. We'll call it a critical point. We'll admit that it might be what we're looking for, and we'll deal with it later. Right? We'll eventually, maybe plug in and check the values and just try to see. Okay, so does this all look familiar? Very important thing to realize is that these three conditions, a lot of people misunderstand and think that if any one of these conditions is satisfied, then that is a maximizer or a minimizer. Absolutely not. The whole point about these conditions is that we don't know what's going on when these things happen. We cannot draw any conclusion at all. Okay, all right, so that said, let's see the multivariable version of this. And it's so similar, and you can even kind of see this coming. And so let's look at a point kind of like this one here. I'm going to take as implied by the picture that I've drawn that these three conditions are satisfied. Notice that point is in the interior. So I can kind of move from there in sort of any direction I might need to for whatever reason. The function's differentiable. So if it's differentiable, that means I can make arguments about derivatives and how the function's changing using our differentiability tools. And let's assume again that the gradient is not 0. In other words, there is a non-zero there is a gradient vector of non-zero magnitude. That gradient vector is pointing uphill in the graph. That gradient vector is pointing in the direction the function's increasing. And if the function's increasing, it is not the maximizer that we are looking for. Notice how this is, again, just a complete rip-off. Oh, come on, man. I want this. There we go. Complete rip-off of the argument we made up here in single variable. Same ideas, just kind of, multivariable instead of single variable. So again, these conditions apply practically everywhere in your domain. I'm going to pretend like I just filled in most of the points there. Right? Most of the points in the domain will satisfy all three of these conditions in most cases, but sometimes they will fail. There are some points, right, for example, that are on the boundary. Right? This point here, in fact, this whole boundary, right? Those are points that are on the boundary. My argument fails. I can't say that I know for sure what's going on at this point, because my argument implies being able to move in the direction of the gradient. I don't know which direction the gradient is pointing here. I might not be allowed to go in that direction because I'm on the boundary. Right? So my argument fails. Likewise, points where there's a differentiability issue, like that one. If I can't use the gradient, then I can't draw any conclusions. I can't eliminate that point. And then likewise, points where the gradient is zero, such as there and there. Likewise, if the gradient is zero, it's not pointing in any direction. And so I can't say that it's pointing uphill. It's not pointing in any direction at all. So again, any time any one of these three conditions happens, we have to admit that we have no idea what's going on. We call these critical points, and we declare that we're just going to come back later and check it out. Try to understand after the fact maybe what's going on at those points. All right. So I hope everybody sees how it's strategically, it's really, look at that, Christmas colors. How about that? I just tell you that. Yeah. Really similar argument. Right? Yes?
Just for the criteria about zero, should we be able to visually see or like...
No, this is algebra. This is algebra. Yeah, you're going to do all this algebraically.
Okay.
Yeah. Right. Absolutely. No, I'm just drawing the picture for a visual aid. Yeah. Right. Okay, so let's see an example. Let's look at this function right here. I'm going to find all the critical points. Notice it didn't ask me what the maximizers are or the minimizers. It's saying just find the critical points. We'll deal with how to identify maxes and mins later. Okay, so let's see here. First condition I have to worry about. Are there any points on the boundary of the domain? Well, the domain is all of R2. There is no boundary, so there are no points on boundary, right? So there's. I don't get any critical points by looking at this interior requirement. Okay, all right. What about? Are there any points where this function fails to be differentiable? It's a polynomial. Polynomials are differentiable everywhere. Whole theorem, chapter 2. So yeah, I don't get any differentiability critical points either. So we move along to the third condition. I need to find points where maybe the gradient's equal to 0. So, okay, let's take the gradient, set it equal to 0. Look at this resulting algebra. And good news, that algebra is actually pretty easy. The first equation straight up tells you x is plus or minus 1. Second equation totally tells you y is 0. And boom, 2 critical points. Right? So, again, what do I know about these points? Basically nothing. All I know about these points is that I don't know what's going on at these points. I can't eliminate them. And what's actually happening? No comment. All right. Okay, now the algebra on that one was easy. I think it's important to note that you do have to be careful that sometimes the algebra can be a little tricky. There are some algebraic landmines that come up. Here's one of them. Let's suppose we were looking at this system instead of the one that we found ourselves dealing with above. It's very tempting. A lot of students make the mistake of thinking that this, in other words, x squared equals y squared, means, I'm going to put a question mark here, that x must equal to y. And that's just absolutely not true. It's a common math crime committed in high school algebra, high school math classes of different sorts. And it's absolutely not true, and it's absolutely not good enough. Right? So if you are perhaps in the habit, if you have been encouraged perhaps in your high school algebra classes to just cancel the squares, yeah, you can't do that. That's really not okay. After all, not hard to see that negative 3 squared and 3 squared are the same, but negative 3 and 3 are not equal. Right? So it's a little annoying. So how do you deal with this circumstance? Good news, it's not that big a deal. You just have to do what we call considering cases. So this implies that one or the other of these two things must be true. You can argue this by factoring, or take the y squared, move over to this side, factor x plus y, x minus y, all that business. But anyway, one way or the other, these are the only two possibilities. And so you just consider them one at a time. And we'll start with case 1. Where x equals y. What would x equals y tell me about this second equation? Well, this second equation, if x is equal to y, turns into this, which I can totally solve for y. Which you can then plug in to the condition and solve for x, and thus get your critical points. That make sense? No big deal, right? You just have to kind of, again, one case at a time, consider what those cases mean. And then likewise now for the second case, looking at this second case where x is negative y, we can plug that into our second equation here, which becomes this, which, again, I can totally solve for y. And again, once you know y, you can now keep in mind, we're going to plug these results for y into the new case that we are currently considering. Don't plug it in back up here. Okay? And if we know y, this formula tells us x, and again, gives us critical points. Okay, so altogether, looking at both possible cases, we have now a collection of what looks like 4, but you will quickly notice one of them is sort of a double count. So, yeah, okay. 3, then, actual critical points. Everybody good? Heads up on the algebra. And keep in mind another thing. There's common misunderstanding in examples, in questions like this. Again, students have this, they've had it ingrained into them from when they were this tall, that it's about the answer. It's all about the answer. And it's not. It's about the reasoning. That's what this class anyway is about, the reasoning. So it could be that the actual maximizer, or whatever the question was actually asking, might be one of the critical points that you would have found even if you had ignored the cases. Not the point. Right? The point is that the reasoning isn't valid, and so you're gonna take a hit points-wise if you don't consider the cases. Right? So make sure to be careful about that kind of thing. Okay, second derivative test. It's actually, again, not that different from the single variable case, but it is a little different. So this one you do have to remember a new rule. In the single variable case, if you're looking at a point where the derivative is 0, that makes this term go away. Then whether or not this is a max or a min is going to entirely be determined by whether this term is positive or negative. And here's the thing, 1/2 is always positive. This square is always positive. Well, it's never negative. So whether this term is always positive or always negative, it comes down to just looking at f double prime. It's as simple as that. So whether f double prime is positive or negative entirely determines whether this is a min or a max. And something very similar works down here. Here is our second degree Taylor polynomial. We'll again consider a case where we're looking at a critical point where the derivative is 0, in which case that term goes away. And again, it boils down to just figuring out when is this expression always positive or always negative. This is just a harder expression to understand. It's not as convenient as what we had in the single variable case. There's a matrix vector product in here and a dot product, and oh my gosh, there's a lot of weird in here. I can't just look individually at the factors. It's just not how that works. That's the bad news. Here's the good news. You'll probably recognize this construction. It's a quadratic form. Right? So this is a linear algebra thing that y'all saw in Math219, presumably. But it remains, I simply need to know, just like I did up here, under what circumstances can I conclude that this is always positive or always negative? Said differently, I just need to know where is this matrix positive definite or negative definite or neither. And then therefore conclude whether it's a local min or a local max or neither, otherwise known as a saddle point. This, actually, you know what? Let me go back to I've got a good picture here. Let's see. There we go. So we call this point right here a saddle point because it kind of curves up in one direction, but it kind of curves, if you will, sort of downward in the other direction, kind of like a saddle. So, terminology. Okay, and again with there we go. Okay. All right. So there is some non-trivial linear algebra that goes into answering this question as to how do I look at a Hessian matrix and decide if it's positive definite or not. And there's some, I want to say some of the more sophisticated linear algebra from Math219 is business about how symmetric matrices are always diagonalizable. I don't know if y'all remember that result from way back when, flashbacks, right? But anyway, there is some linear algebra arguments that you can make. This is the highlights if you're interested. This isn't a linear algebra course. I'm just going to point out that there is some linear algebra reasoning that you can work your way through if you'd like, and I encourage that, but it's not something you're responsible for in this class. What you are responsible for is the punchline that it boils down to, and this is called the second derivative test. This is what results from that linear algebra argument, and it goes like this. First, you have to look at the determinant of the Hessian matrix. That's weird. This is just how the diagonalizability stuff works out. Look at that determinant. If it's positive, then proceed to this little chart over here. If it's negative, you have a saddle point. And if it is 0, then you have a failure, and the second derivative test crashes and burns, and you draw no conclusions at all. Now, looking at the second part of the test, in the case where the determinant is positive, here's the good news. This starts to really look like the single variable second derivative test. You look at the x second derivative. You could use the y if you prefer. It doesn't matter. I'm using the x just for alphabetical order reasons. But positive implies a min, negative implies a max. So kind of familiar looking. Some sense. And again, algorithm. It's a plug and chug thing. So let's apply that algorithm to this example. Let's see how we're doing. I think we're all right. We previously looked at this function. We found the critical points. Namely, we have already found points where we have no idea what's going on. Right? Again, that's the whole idea of critical points. We have no idea. Are these maxes or mins or what do we got here? So the second derivative test is going to help us clarify this. And here we go. Notice I just write down the Hessian matrix. right? And then I'm just going to take my 2 points one at a time and plug into the rules. And let's see, why don't I try to get all this onto the page? Onto the screen. Here we go. Oh, I should do this. There we go. A little bit more space. So let's look at this point here, -1, 0. Right. At this point, I can plug in and see the determinant is negative. Negative means saddle. So this first critical point is saddle point. See, very pluggy-chuggy, right? It's just follow the rule, right? Follow the test. Okay, next, let's look at 1, 0. Well, 1, 0, you plug into your Hessian formula, you see it is positive. Now, again, that alone does not answer the question. But it tells you what to do next. And what we do next is we look at the XX second partial, which is this right here, fxx, top left element of the Hessian matrix. You can see that it is positive when you plug in this point B. And if it's positive, that means local min. Pluggy-chuggy. Does everybody see how that works? Okay. All right. Next question. This is a subtlety. A lot of people mistakenly think that if you have a function with a domain, if you eliminate most of the candidates as possible maxes, then whatever remains must be the max that you're looking for. If there is a max, then that's true. Right? Process of elimination. It's well known. It's a good method called process of elimination. But the problem with process of elimination is it doesn't work if the thing that you're hoping to find doesn't exist in the first place. Right? Process of elimination will just leave you with some basically random point that you just couldn't eliminate, but you don't want to conclude that something is the thing that you're looking for if the thing you're looking for doesn't exist. Right? So that's a real problem. For example, let's look at a situation like this, where there's kind of an open-ended left endpoint for our integral. This is single variable, of course. If you have an open left endpoint, the function can just get continually bigger and bigger as you approach that endpoint. There is no maximum to be found. So process of elimination can't find it because it doesn't exist. Right? So you got to watch out for that. Let's see, here's another possibility. What if your domain is unbounded? It just goes off to infinity in one direction or the other. Well, then the function could just keep getting bigger and bigger. You can go as far as you want in that direction. The function could run off to infinity. Again, there is no maximum to be found. Okay. Third possibility, what if your function has a discontinuity? Well, then we don't even care about the domain. If the function has a discontinuity, there's nothing stopping that function from just approaching infinity on kind of one side of an asymptote. Or both sides, perhaps. Whatever. Again, there is no maximum to be found. So what we have down here is a theorem that helps us address this. And in particular, if your domain is closed, namely none of that nonsense, and if your domain is bounded, in other words, finite, and I like to think of it as it can be put inside of a ball or put inside of a box. It doesn't run off to infinity in any direction. So in other words, none of that nonsense. And if your function is continuous, in other words, none of that nonsense. If these three conditions are all satisfied, none of these shenanigans are possible. And it turns out, in some sense, these are the only possibilities. These are the only ways in which a function can fail to have a maximizer. And so if none of these things happen, in other words, if all three of these conditions are satisfied, then there is a global max. And then your process of elimination makes sense. Okay. This next thing is an attempt to deal with, how do I deal with the boundary, right? We know how to deal with interior points, but what do we do with boundary points? I did this algebra here because I wanted you to see what we're going to be able to get rid of, what we're going to be able to bypass, because this algebra stinks. And this isn't anywhere near as bad as it could have been, right? So we're not going to go through this algebra, right? We are very short on time. We're going to go straight to what the better method is. The better method is called the method of Lagrange multipliers. So very, very clever idea. It addresses the boundary problem. It addresses a larger category of problems. Namely, suppose you just have a constraint. Actually, I wanted that in blue. Sorry. So it's one thing to look at a function f and say, hey, I want this to be as big as possible. It's another thing to say, look, my inputs are not entirely independent of each other. My constraint here has to be satisfied. I'm only interested in what's happening where my constraint is satisfied. And subject to that constraint, now how big is it possible for my function to get? Right? This is a much harder problem. And it doesn't really have a single variable analog. Quite. So there's a function you want to optimize, but a constraint that has to be satisfied. So for example, you might say, hey, let's find the point closest to the origin. Oh, wait. Now, again, you're not allowed to just pick any point you want. Only points on this curve. And among just the points on this curve, which one's closest to the origin? Very different question. Okay. So what we have here is an example where we have a constraint and thus a constraint function. The constraint function is the function whose level set gives you the constraint. And then we have the objective. Objective function. The function we're trying to make as big as possible or as small as possible, whatever the case may be. Okay. So there's a million versions of this and a couple of practical ones. Just try to persuade you that this is relevant to everyday, non-abstract considerations. Here is a reasonable practical question. I've got a certain amount of area that I can work with. Maybe I'm working for Amazon and I'm making boxes to ship stuff in, right? And I want the box to be as big as possible, given the amount of cardboard that we can afford to spend on this problem. That's a reasonable question, very practical question. And notice there is a function that I want to make as big as possible, and there is a function that is constrained, right? The area has to be fixed. In other words, we're looking at a level set. We're looking at a constant value of that constraint function. Okay. Likewise, let's suppose we run a little small business or something, and I want to figure out how to, run my business with maximum. Maybe you want to maximize productivity. Maybe you want to maximize profit. Whatever. Okay. So in this case, we want to maximize productivity. Whatever your productivity function is, that's your objective. That's what you want to make as big as possible. But we have these constraints of reality. I have a limited budget. I only have so much money. I can't go out and hire 10,000 people. I can't afford that, right? So the budget then is your constraint function. Does that make sense? So one of the big problems that happens when you're doing Lagrange multipliers is the way we're going to address this momentarily, is to conflate these functions. And it is a little confusing because most of the time we do optimization, there's one function. That's the function we want to make as big as possible. That's the function. Now we unavoidably have two functions that serve critically different roles. Sorry about that. Does that make sense? So make sure to keep these distinct in your mind, right? And that's why we have terminology for them. There's the objective function, and then there's the constraint function. Okay. All right, so here's the big idea. Big idea. under a certain set of conditions, I can conclude, I know with complete confidence something, and thus the green coloring. I know with complete confidence that the point A is not the maximizer that I'm looking for. There is an elimination tool. So it's not that different from the single variable optimization we saw. The difference is in what the conditions are. The conditions, I need both functions to be differentiable so that I can make, chapter 2 kind of arguments. That's the first condition. Secondly, let's see here. Let me color code better. Secondly, I'm going to need the constraint gradient. The gradient of my constraint function, I'm going to need that to be non-zero. You'll see why in just a moment. The basic idea, though, the reason I need my constraint gradient to be non-zero is because I need for all multiples of my constraint gradient to actually define this line perpendicular to my constraint set. And remember, an old chapter 2 result is that gradients are always perpendicular to level sets of that same function. So I need this to be non-zero so that its multiples define this perpendicular line. And then the third thing that I need for my objective gradient not to be on that line. Right, so if this happens, if these three conditions are satisfied, in other words, if I have this picture, then again I claim, you can even kind of just glance at the picture, I claim there's absolutely no way this could be the maximizer we're looking for. Couldn't be. Check it out, the function's increasing as you go that way. Okay, now I'm not allowed to go that way. I have to stay on my constraint set. But I can certainly go kind of somewhat in that direction. And if I am moving in that purple direction with this blue gradient, then I have an acute angle there, and the directional derivative is positive, the function's increasing. This is not the maximizer we're looking for. That makes sense to everybody? Okay. All right. So, good, cool, good news. That's satisfied by most of the points in your domain. And again, you just have to keep track when one of these fails. And so if either of these functions fails to be differentiable, if the constraint gradient is zero, then I got a problem with geometrically with that perpendicular line. If the objective gradient is not a multiple, right? So in other words, if my objective gradient is a multiple, then again, problem. And so these are the points that I don't know what to do with. I can't eliminate them. They might be the maximizers we're looking for. I don't know. We call them critical points, and we'll deal with them later. Okay. All right. So let's see some examples. Let's see here. I have like 2 minutes. I think I'm going to have to give you all some more videos. I'm not going to be able to do the 3 examples I was hoping to do in the next 2 minutes, but let's do what we can here. Notice first we have to identify what is our objective function. I'm looking for the highest point on a given surface. That means I want the greatest value of z. That means z is the function I want to be as big as possible. Z is my objective function. And then I have a constraint. My constraint is that this equation must be true. Notice this is written as a level set, and so I can just right away determine that this is my constraint function. And now what I'm going to do is just go through, again, checklist, just one at a time. I'm going to go through this checklist of potential problems that could give me a critical point. I'm going to look for a differentiability failure. I'm going to look for where the gradient is 0. And I'm going to look where the one gradient might be a multiple of the other gradient. By the way, this is what's called the multiplier. This lambda here is the multiplier, and thus the term Lagrange multipliers. Okay, so let's see here. These two functions. Whoopsie. do these two functions have any differentiability failures? Is there anywhere where these points fail to be differentiable? They're polynomials, they're fine, so no critical points there. By the way, again, I know this is going to sound silly, but this is important to the sort of the philosophy of the course. But again, it's not about answers. It's about reasoning. This is not a waste of time, writing down that these are both differentiable. This establishes that you've done the proper reasoning, that you have considered the possibility of differentiability failures. You have to write this down. This is worth points. Now, again, you can take a cynical point of view. Why should you count off for me leaving off some little thing? Take the glass as half full empty. Free points. Take them. This is a good thing, right? Free points. Second question. Is there any point where the constraint gradient, here's my constraint gradient, is there any point where that's equal to 0? Well, a little bit of linear algebra. Whoops. Yeah, come here. A little bit of linear algebra allows me to rewrite this as a linear transformation, thus a matrix. Wondering where that's equal to 0? I have a Math219 problem. Right? You row reduce or make a invertibility argument with the determinant. Take your pick. Right? I like the determinant approach because it's quick and easy, especially in a case like this. Right? But anyway, check it out. We kind of do have a point, right? X equals 0. And it's tempting to say, and your first instinct would be to say, yeah, we found a point where our constraint gradient is 0. That should be a critical point. Here's the thing. Keep in mind, though, I'm only interested in eliminating points that are actually on my constraint set. I don't need to eliminate points that are not on my constraint set. In other words, I don't care about finding points that aren't allowed anyway. I don't need to eliminate them at all. So I'm going to ignore any points that I find that don't satisfy the constraint. And here's the thing. That point does not satisfy our constraint. I have no need to eliminate it. It'd be pretty silly to call that a critical point. It'd be pretty silly to claim that I don't know what the function's doing at this point. This function's not even allowed to be entertained by the question in the first place. So you do have to reason through and find that point and then say, yeah, but not our problem. And I'm definitely out of time. Okay, I'm going to send y'all recordings where I'll go through all 3 of these examples that follow in detail, and see y'all on Friday. Have a good one.